Hello everyone, my name is Konstantin Vladimirov and today we continue our master's course at MIPT. In this lecture we are going to talk about smart pointers in C++, both the standard ones from the library and also some patterns that are not officially standardized, but still appear in real code. And this topic is not extremely hard. Today will be easy lecture compared to what is following and what was in previous lectures. But it is really important because smart pointers are really about ownership, resource management, exception safety. So today we'll build the correct intuition step by step. And let's start with a simple question. Who owns the memory? This question might sound rather philosophical, but in C++, people often say things like, this object owns the resource, or ownership is transferred here to there. And what does that actually mean? Before we continue, pause the video for a moment and think, what is the real definition of ownership in C++? How would you define it? 3, 2, 1. Okay. And here's simple practical definition. Memory is owned by whoever allocates it and deallocates it. Or more directly, the owner is the one who has the responsibility to destroy the object and free the resource. So in C++, ownership is basically defined through destruction. Now look at this example. We allocate an object with new, pass the pointer into some function, and then delete it. And at first glance, it looks correct. We exercised our right to delete it. We are owning this P. But pause the video and think, what can go wrong here? The first problem is that foo might store the pointer somewhere. Then after delete, we get a dangling pointer and use after free. But even worse, foo might throw an exception. In that case, delete is never executed, and we get a memory leak. So manual new and delete are dangerous, because ownership is not represented in the program itself. It exists only in our heads. And of course, we want to make ownership explicit and automatic. Now let's look at the ideal situation, value semantics. Here we create the resource directly as a local object on the stack, and then we just use it. Look, like this. Simple like this. Simple like std_vector, I would say. If we can write code like this, then we are basically done. This is the best possible design. Why? Because now who owns the memory? In this case, the compiler owns it. With tag objects, you cannot really mess things up easily. The compiler allocates the storage, the compiler releases it, and destruction happens automatically no matter how you exit the function. Even if we return early or throw an exception, the destructor is still called. So value semantics is always the first option. If it is possible, this is the cleanest and safest solution. But of course, value semantics is not always possible. Sometimes we need dynamic allocation or polymorphism, or we want to hide implementation details, or the object is simple too expensive to copy, and then we use a standard approach to resource management in C++, which is RAI. Resource acquisition is initialization. The idea is simple. We wrap the resource into some class, and that class becomes responsible for cleanup. So in this example, make RAI pointer allocates the object, and that RAI pointer owns it. And the most important part is what happens when we return. If we return because of some condition, the destructor is still called automatically and the resource is released. So RAI gives us the same safety as stack objects, but for dynamic resources. And now, if RAI is so powerful, why don't we have a simple standard class like this one? A class that stores a raw pointer, deletes it in the destructor, and supports deep copying. So if you copy the wrapper, it allocates a new object and copies the value. If you move the wrapper, it just transfers the pointer. At first glance, this looks like the perfect universal solution. I would say zero option. It is copyable, movable, safe, and have automatic destruction. So why is there no such standard class? And the answer is, please think about it for a moment. 3, 2, 1. Okay, I hope you did. And the answer is because it doesn't really solve a new problem. If your type is already copyable and movable in a reasonable way, then you can usually store it directly as a value on the stack or inside a container. This is just the same value semantics we saw one slide earlier. This copying pointer is basically value semantics just implemented in more expensive way. And yes, it works, but it adds extra allocation, extra indirection, and worse performance. So the absence of such class in the standard library is not an accident. It is a design choice that pushes us toward better solutions. Value semantics first, wrappers only when value semantics is impossible. And in this course, we will see many examples of objects where value semantics is impossible. For example, you cannot make value semantics for like mutex. There is no meaningful way to copy mutex. So in such cases, smart pointers and ownership abstractions become necessary. Okay, so at this point, we can list the reasonable ownership strategies that actually exists in C++. First, the ideal options is value semantics. The object is stored directly and the lifetime is managed automatically. If that is impossible, then we start using pointer-like wrappers, and we have a few realistic design choices. We can disable both copying and moving, which gives us strict unique ownership, or we can disable copying but allow moving, which is still unique ownership, but now the object can be transferred. And then we have shared ownership, reference counting with an external control block, and intrusive reference counting, where the counter lives inside the object itself. And that's basically it. There are no other fundamentally different strategies, and what is interesting is that in the standard library we mostly have only two smart pointers that cover this space, unique pointer and shared pointer. And now let's look at very simple non-copyable object. Here is a scoped pointer. It holds raw pointer, but both copying and moving are disabled, so it is not copyable and not movable. So it's now a simple question. In which cases can such an object still be passed and returned by value? Because at first glance it seems like the answer should be never. But in modern C++, the real answer is more interesting. By the way, how do you think? Why there are no this class in the standard? You might either wait for end of this lecture when I will answer this, or just guess now and maybe write your answer in comments. Okay, so in modern C++, the real answer is more interesting. The trick is prvalue elision. In some cases, the language allows the compiler to construct the object directly in the final destination. So even if copying and moving are deleted, the code still works. For example, we can pass a temporary scoped pointer into a function by value, and it compiles. We can also return a temporary scoped pointer from a function, and it compiles. So why does it work? Because there are PR values. Peer values are not real named objects yet. They are basically recipes for constructing an object, and the compiler is allowed to skip the move entirely and build the object directly where it needs to be. But notice the last example. If we create a named local variable t and return it, this is a different case. Now t is a real object with an identity and a lifetime, and here we need an array. But an array is not guaranteed in the same way. So this return statement can fail to compile because it requires a move, and move is deleted. This is one of those cases where understanding value categories is not optional. It directly affects what code is legal, and I personally find this really funny. This is legal, this is not, but these are the same. This class still have no copy or move constructor, and in this case, copy or move constructor will be probably elided by compiler. But in this case, this is purely illegal. Okay, and so now let's take one step forward. What if we allow moves? Do you have any real-life examples where move-only types are useful? This is not a theoretical question. In modern C++, this is one of the important patterns. So pause the video for a moment and think, and write down in comments, where do you actually need a movable but a non-copyable object? Maybe you may tell us some story from your career where you did need it. So go ahead. Okay, and if you want to enjoy the show, this brings us to the idea behind unique pointer. We store a row pointer. Copying is disabled because copying a row pointer would mean two owners, which would lead to double delete. But moving is allowed. And please note, this is not stud unique pointer class. This class is far from stud unique pointer. We will make it closer in the couple of next slides. So moving transfers the pointer from one object to another, and the old object becomes empty, usually by setting its pointer to null. And move assignment can be implemented with swap, so unique ownership is still preserved, but now it can be transferred safely. And now, once we have a movable type, returning by value becomes much easier. If we return a named object from a function, the compiler automatically treats it as a move. So return t will produce a move construction here, and everything works. Why? Because bus braces is peer value expression. So this is peer value, this is move construction. Great. And the important detail, you do not need to write stud move here. In fact, returning stud move of t changes the meaning of expression. Instead of returning the value, you are now returning an x-value reference, and that can easily become dangerous or pointless. So the general rule is simple. If you return by value, just write return t and enjoy your move semantics. And the language already knows what you mean. But we are here in the master's course, and we need to be ready to some tricks. So tricks will follow. Let me ask a slightly provocative question. Can we imagine a situation where writing stud move in a return statement is justified and actually beneficial? Because normally people say never do this. I just said never do this one slide earlier. And most of the time this is correct. It is either redundant or it blocks optimization. But let me show you a rare and interesting case where this is actually profitable. Like, let me show you. Rare and interesting case. I hope you can see my browser now. Yeah, you can. Yes. And see this. We have this full structure with deleted copy construction and enabled move construction and with some append method. And we are pretty sure this append method returns something like dereference this, like this one. We are pretty sure it is. And we have basically two variants of writing append foo. First variant, I call it implicit move, is just return f. We are calling append and just returning f by value. And enjoy our move semantics. And second way is calling f append, and we are sure it returns itself. It returns this object. And we are returning this result. So semantically, this is the same. Let's see how compiler will optimize it. So let's see Clang and bingo. With explicit move, this code is beautiful, but with implicit move, this is madness. We spent 3 times of stack on it. So why does it happen? How do you think? Please think a little. What's wrong here? Why compiler optimizes this far better than this? And the answer is simple. Compiler basically don't know that this method is returning pointer to this. This method may return any reference to any object, in theory. And compiler need to be conservative. Compiler need to guarantee that these objects outlive this function call. And compiler spills it to the stack and then fills it. And this is basically a game changer. Okay, I believe this was mind-blowing enough. So now we have a movable unique pointer. And this means we can finally do something like transfer ownership out of current scope, like this one. In this example, we acquire a resource with new, store it in our unique pointer, and later, if some condition happens, we explicitly transfer ownership into another function using studMove. This is the key point. The bar now becomes the owner, and our local pointer becomes empty. We just transferred ownership. If we want to transfer it again, just move it again from bar. And that's all. And if we do not transfer ownership, then nothing special happens. The resource will be released automatically in the destructor at the end of the function. So this is already a huge improvement compared to raw pointers. Ownership is explicit and safe. And now in real code, we almost never want to write new directly. So naturally, we want to have a function similar to something like studMakeUnique, like on this slide. Implementing it is straightforward, and I believe you can do it by yourself, but you may enjoy this slide. Just a template that perfectly forwards arguments into the constructor of T. And this is basically the same transparent wrapper idea again. We allocate with new, forward all arguments, and return the unique pointer by value. So far, it looks perfect. But here is a good question. Do you see any subtle issues? Can there be a situation where we can create a unique pointer manually, but make unique just will not work? And if you think a little, it is rather hard, but if you think a little, you will come with this solution. Imagine a type with a private constructor like this. A do have private constructor. And inside the class, we are allowed to call the private constructor so we can write new A of val directly. But makeUnique is a free function. it is not a member of the class and it has no special access. So it cannot call the private constructor and compilation files. Ta-dam! These cannot be called. And these can be because constructor is inside the scope of the class. Even if the compiler would inline everything later, access control is checked before inlining, far before backend, so this is still ill-formed. Though this is really the limitation of make unique, it is not always usable, but we may ignore it as a corner case, okay? And now let's generalize the idea. In the most general case, we do not even have new and delete. We just have some abstract resource like this with two functions, create and destroy, and the resource might not be copyable at all. And this is very common in real system programming: file handles, sockets, mutexes, OS objects, library handles, and so on. So our smart pointer design should be able to handle this kind of API as well. And now, here is an important design option. Instead of hardcoding delete, we can make the deletion logic a separate template parameter. So the pointer stores two things, the raw pointer itself and a deleter object. And then the destructor just calls the deleter. This makes the class much more general. We can destroy objects using delete, delete with square brackets, free, close, or some custom destroy function. So now question is, what could default delete look like? And the simple version is just a function object with operator braces that calls delete. And what about arrays? If we allocate them with new square brackets, we must deallocate with delete square brackets. So if you write unique pointer of in square brackets, the default deleter must call delete square brackets. This is why in the standard library, default delete is specialized. One version for T and another for T square brackets. And this is exactly one of the reasons why unique pointer is a class template with special behavior for arrays. So at this point, we already see that implementing a correct unique pointer is not just wrap a pointer and hold delete. There are many subtle corner cases, and the standard library design reflects that. And what is most important, this is still not a std unique pointer, because we do have this offending deleter field. Now, there is one important practical detail in this design. If we store the deleter inside the unique pointer object, then the deleter affects the size. And this can easily make our smart pointer bigger than a raw pointer. So the question is, does a unique pointer always have to be larger than a raw pointer? Ideally, no. In many cases, the deleter is stateless, and we would like the pointer wrapper to still be just one, like machine word, like pointer size. I don't know how to say this. So how can we store the deleter without paying extra space in the common case? And this is not just an academic question. This is exactly the kind of detail that separates a TOE implementation from a real standard library implementation. And if you want to say me just like inherit from this class and use empty base class optimization, then think again. This may be a function. This may be a function pointer. How would you inherit from the function pointer? So if you want to answer me, okay, let's just do some smart wrapper on the template magic that treats function pointers and wrap them and inherit from this wrapper and delegate to it, okay, but maybe we do have something like this already in standard library. And answer is yes. And it is like mind-blowing, I would say. Welcome, stud tuple. Yes, this is a really elegant solution. we are storing the pointer and the deleter inside an internal tuple. Because tuple already uses CBCO, empty base class optimization. So if the deleter is an empty type, it takes 0 extra space and the whole unique pointer object becomes the same size as a raw pointer. And if the deleter is stateful, then yes, we store it and pay the cost honestly. So tuple gives us a very practical implementation trick. It automatically compresses empty objects. And by the way, if you ever looked into the implementation of tuple, it is an absolutely terrifying piece of template metaprogramming. But the nice part is you don't need to re-implement it. You can just use it. And now let's connect this lecture to the previous one, where we discussed allocators and PMR. And here is a very interesting setup. We have bar which contains a PMR string. I mean this one. And then foo contains a standard unique pointer to bar created by using makeUnique. And now we store foo object inside the PMR vector. And the vector uses custom memory resource, like test memory resource, that logs all allocation. And now a simple question, what gets printed? Try to guess. And 3, 2, 1. And let me show you. You might expect that all allocations will go through. This is test memory resource. It just like logs. And you might expect that all allocations will go through this test memory resource. This one. And this one. And these have really long data to not fit SSO. And we shall see this allocation. But in reality, we see only 8 and then 16 for stud vector and 42 for PMR string. But we do not see the memory used by unique pointer. And that is a problem. First to know this problem in public was David Sankel, and I believe I will have Sankel's talk in my bibliography. If not, please Google Sankel on allocators. The allocation inside makeUnique do not uses PMR allocator, do not uses test resource. It just uses global operator new. Only the PMR string allocation inside bar uses the default resource. So we do have stud vector allocation, we do have stud makeUnique, and we do have PMR string allocation. And stud makeUnique allocates string structure itself, and string allocation allocates the string contents. And the string allocation is inside PMR because string is PMR here, and our vector allocation is PMR because vector is PMR here. But this stud makeUnique that allocates rather large, I would say like 40 bytes to string object, because to PMR string object, because you might remember that string is huge. It have like size, capacity, data pointer, some stuff to enable SSO. Yes, all this goes through global new and delete, because unique pointers are not allocator aware. And even though PMR vector is scoped vector, it has scoped allocator, its allocator shall allocate everything we allocate underneath that vector. These just don't work this way. Okay, great. Now how to fix it? How to make our wrapper, at least wrapper around unique pointer allocator aware. And this is easier than you think. So The standard library, of course, does not provide PMR unique pointer, and let's build it manually. The simplest idea is to store a unique pointer with a custom deleter. This is polymorphic allocator delete. And this custom deleter will store the polymorphic allocator. And then foo can allocate bar using that allocator, and the deleter will destroy and allocate it correctly. Like this one, we are just providing this allocator to polymorphic allocator delete, which means that polymorphic allocator delete must be implicitly constructible from stud polymorphic allocator of byte. Okay, let's show the code of this deleter. This is polymorphic allocator of byte, and this is implicit conversion constructor, and this is deallocation. Allocation destroy, allocation deallocate. And of course, construction will be this way. We receive an allocator, store it inside the deleter, allocate memory for bar using alloc.allocate, construct the object, and then reset the unique pointer. This one. So now ownership and allocation are consistent, and the interesting part is the output. Let me show you. This is the output. This is test resource, and this is PMR vector, and we all have in place back. And this is, as I showed, the unique pointer with stateful deleter, allocate, construct, reset, and here destroy, deallocate. Okay, everything as on slides. And now, sorry for this, it was accidentally, yes. And now, what do we see? Yes, we do see real picture. 1640 for stud string, 42 for string contents, 32 for stud vector reallocation, 40 for another string, and 42 for another string contents. Now we do see a real picture. Okay. And this is one of those cases where the standard library gives you the tools, but it does not automatically save you from misuse of tools or from mistakes. And now let me follow a classic example popularized by Herb Sutter, a tree where I will have talk of Herb Sutter in my bibliography, I believe, a tree where every node owns its children via unique pointer. At first it looks very clean. Ownership is obvious, destruction is automatic, and you get strong memory safety guarantees. Like this one. But then you immediately hit a practical question. What should find return? Think about it for a second. You want to locate a node by position, and you want to give the caller access to elements stored in this node. What do you return from find in a tree implemented with unique pointer? If you return a raw pointer or reference, you basically punch a hole through a safety story. The caller can store that pointer that we can later destroy, reorganize nodes, and now you have a dangling pointer. If you try to return a unique pointer, that makes even less sense, because unique ownership means you cannot have two owners. Of course, reference to unique pointer or pointer to unique pointer is like hell. I will not even consider such solutions. But if you return unique pointer, then this unique pointer owns all the subtree, yes, and it is also a mess. So the uncomfortable conclusion is unique pointer is great for ownership inside the data structure, but it's not great for like handing out stable references to elements. And so the next idea is obvious: use shared pointer for nodes. Then find can simply return a shared pointer, and that keep the node alive as long as somebody uses it. But now there is a serious problem. The node becomes part of our public API, and node is an implementation detail. The user of the tree should not even know that node exists, and even worse, if you expose shared ownership of nodes, you also make it much harder to change the internal structure later. You're basically forcing the whole design of the tree to be organized around shared ownership. So yes, it works, but it leaks abstraction and locks you into a particular representation. And first, before we will understand how to fix it, let's recall how shared pointer roughly works. A shared pointer, and please don't believe this picture. I will redraw it this soon. Shared pointer does not directly own the object. Instead, ownership is managed by a separate structure called the control block. The control block contains the reference counter and the deletion logic, and it keeps the object alive as long as the count is non-zero. All shared pointer instances point to the same control block and can increment and decrement the counter. And this picture is simplified, but the main idea is correctish. A control block is the real owner. And there are two common ways to construct a shared pointer: make shared and new node. And with make shared, the control block and the object are typically allocated together in a single allocation. And in this case, the object is allocated first, and then the control block is allocated separately inside the shared pointer constructor. So these two forms are no longer equivalent, like with unique pointer. They have different allocation behavior, and that matters for performance and for cache locality. And this explains the second picture. With make shared, the object can be stored inside the control block allocation together with the counter and everything else. And so you get one allocation instead of two. Again, don't trust the details of drawing too much, but this is the key point which is true. The control block can contain the object. And now please look at this picture again. Control block pointer points to control block which have node inside it, and let's return to the tree problem. If find returns shared pointer of node, we can keep a node alive, but we don't want node. Node is not part of the interface. It is just how the tree is implemented internally. So how do we return a shared pointer to the data while still owning the node alive? And this is shared pointer has like killer feature, aliasing construction. You can take the shared pointer of node, like this SPN, that we found during the search, and construct a shared pointer of data that shares the same control block but points to a sub-object inside the node. So the control block still owns the whole node. The node will stay alive as long as the returned shared pointer of data exists, but the pointer stored inside the shared pointer points directly to the data member. So we keep ownership correct, and we also keep the abstraction. We expose data, not node. And conceptually, it looks like this. The shared pointer of data still points to the same control block, so the lifetime is managed exactly the same way. But its data pointer is not the beginning of the allocation anymore. It points somewhere inside the node object. So aliasing construction lets you separate two things: what you point to and what you own. You can point to a sub-object while ownership is still managed by the control block that owns the entire node. And for complex data structures, this is really useful. Your control block pointer keeps it alive. Your data pointer points to sub-object, the part you can expose through your interface. Great. I believe it's great. And now, shared pointer comes with its own class of problems. And this is one of the most important ones in terms of ownership. Imagine you have a row pointer n, and then you create two different shared pointer objects from that same row pointer. What happens? Each shared pointer constructor creates its own control block, so now you have two independent reference counters, both thinking they own the same object. And when both shared pointers leave scope, they will both delete the same memory. So, with just 3 lines of code, you can recreate the exact double delete bug that reference counting was supposed to prevent. Like, you see, we do have shared pointers and we still have double free corruption case. Isn't this pity? And this is one more reason why make shared is so strongly recommended. Make shared guarantee to create the object and the control block together, and you simply cannot accidentally attach a second control block to the same object. Do you agree? And of course, you see how am I smiling? And this smile means nothing good. Because you cannot trust even make shared. Let me show you the same situation with make shared. Ta-da! Suppose node wants to share itself. It creates shared pointer from this, and at first glance it might look reasonable. I already have this pointer, I'll just wrap it up. But this is a serious mistake because this is a row pointer. And now, by doing share pointer of this, you create a second control block for the same object, which was in the first place obtained via make shared. So make shared doesn't help, doesn't save you. You still have double free or deletion problem. So the real rule is simple. Never create shared pointer from this directly. But then what to do? And you need some magic, some secret ingredient, like enable shared from this CRTP base. If a type inherits from enable shared from this, it can safely produce a shared pointer to itself using this shared from this magical call. And the reason it is safe is that shared from this doesn't create a new control block. It reuses the existing one. So the natural question is, how can this possibly work? How does shared from this find the correct control block? Let's think about it. Let me show you the architecture. I believe it is brilliant. Conceptually, enable shared from this, when you inherit it from it, brings to your class some weak link, some control block pointer, but this is like weak pointer, whatever it means. And when a shared pointer is created for that object, the shared pointer constructor, because enable shared from this modifies your constructor, shared pointer constructor can detect that the object supports enable shared from this and initialize that internal link. Like enable shared from this, if you inherited from it for your type, it informs your type it was inherited from enable shared from this for your type, and constructor of your type knows that you might be inherited from enable shared from this if you are shared pointer. And if you are, then constructor initializes this internal link, and later shared from these users use that link to create a new shared pointer that shares ownership with the original control block. Isn't it great? An important discussion point here is, can that internal control block pointer itself be a shared pointer? And no, it cannot. If it were a shared pointer, it would participate in reference counter and could keep the control block alive on its own, which creates circular ownership and breaks the model. So internally, it has to be something like a weak pointer or an equivalent non-owning handle. The object must not own its own control block. it even sounds fun. Okay, and now here is a subtle misuse case. Suppose you have a node which inherits enable shared from this, but you create the node as a normal stack object, like this one. No shared pointer ever existed to begin with, so no control block was created, and then you call shared from this. What should happen? Before C++17, this was an undefined behavior, and basically everything happened. Everything exploded, I believe, because the internal link was never initialized. But in C++17 and later, it is no longer UMB. It throws stood, bad, weak pointer exception. And that's actually a very good change, because it turns a silent time bomb into a visible error. So the correct usage is the object must be created under shared ownership from the beginning. For example, if you create it with make shared, which creates the control block and initializes the enable shared from this machinery, and only then shared from this is valid. But notice what this implies. Once you introduce enable shared from this, you also introduce a discipline. You must never create this object normally. You cannot allocate it on stack or global member. You basically force this type to live on the heap under shared ownership. And this is one of the reasons why active use of shared pointers tends to spread. Once you start relying on it, more and more code has to follow the same ownership regime. Like, think about it for a little. How can I guarantee that this node will never be allocated on stack? Of course, with private constructor. Great. So, let me say, if you do have private constructor, then the factory method became attractive. You do have factory method create. If you really want to enforce the correct usage, and now users cannot accidentally create an object on the stack. They must go through the factory, which guarantees that the control block exists, and shared from this will work. It is a bit frustrating that doing it right is slightly harder than doing it wrong. But this is the reality of shared ownership in C++. It is powerful, but it comes with sharp edges and often requires guardrails. And this is also why people sometimes joke that shared pointer is how you slowly turn C++ into Java. Once everything is shared, everything lives on the heap and ownership becomes global. That's not always bad, but you should treat it as a serious design choice, not as a default. Now, there's another subtle point about shared pointer that many people don't realize at first. Row pointers are covariant to generalization. If B is derived from A, B pointer can be implicitly converted to A pointer. We do it all the time. This is essence of the Liskov substitution principle. But template classes, like shared pointers, I believe, are invariant. Even if B is convertible to A, it doesn't automatically, like with pointers, mean that shared pointer of B is convertible to shared pointer of A. But considering aliasing construction, in some sense they are. Like, they need to be, because inside shared pointer of B there is a sub-object of shared pointer of A, and theoretically we can, with aliasing construction, return pointer to this sub-object. If you think about it, it's not obvious at all, because shared pointer is still a pointer-like object. It still behaves like pointer. It can be pointer to sub-object holding the same control block, unlike the unique pointer, by the way. So, question is, if we have a shared pointer of B, how do we obtain a shared pointer of A? And the answer is standard library provides special casting function. We can live without special casting function, just write like more code, but special casting functions are great. We do have static pointer cast, dynamic pointer cast, and const pointer cast. They work exactly like the corresponding casts for all pointers, but they preserve shared ownership. So static pointer cast will perform a static cast to the stored pointer, but it will keep the same control block, meaning the reference counter stays shared, and the object lifetime is still managed correctly. This is actually very similar to aliasing constructors. We create a new shared pointer that points somewhere else, but ownership remain attached to the original control block. So shared pointer has its own little casting subsystem. And it is important to know that it exists. And now let's switch from mechanics to design philosophy. Sean Parent has a famous quote, "Shared pointer is as good as a global variable." Do you have any counterarguments? 3, 2, 1. I believe you do. Because at first glance, it sounds exaggerated. Shared pointer is clearly safer than a global variable, right? It has deterministic destruction, it manages lifetime, it prevents memory leak. So you might feel that the quote is unfair. But there is a full quote. Shared pointer is as good as global variable when it comes to being able to reason about code that uses one. And now it becomes much harder to argue, because shared ownership means that the object can stay alive for an unknown amount of time. And you often cannot tell from local code who else is holding a reference. A shared pointer can be copied anywhere, stored anywhere, captured by lambdas, passed into callbacks, and suddenly lifetime becomes global. In that sense, it behaves like a global variable, not because it is literally global, but because its effects are no longer local and predictable. So yes, shared pointer solves lifetime problems, but it introduces a different kind of complexity. Reasoning about ownership becomes much harder. And this is why shared pointer is powerful, but it should not be treated as the default smart pointer. And now there is one more important feature we discussed for unique pointer, but we haven't discussed yet for shared pointer. And this is custom deleters. With shared ownership, this becomes even more important because the moment when the resource is actually released is often not obvious at all. With unique pointer, destruction happens at the end of the scope, and you can usually see it through magic glasses, but whatever. With shared pointer, the resource is released when the last owner disappears, and then that might happen in a completely different part of a program. So if you use shared pointer, you really must be sure that the resource is destroyed correctly. Now, can shared pointer manage something that is not allocatable with new? Absolutely. For example, consider SDL load bitmap. It returns an SDL surface pointer, but this resource must be freed using SDL free surface, not delete. So a plain shared pointer with a default deleter is clearly wrong here. Instead, we can pass a custom deleter as the second argument. And this is a very common pattern in real code. Shared pointer is used as a general resource handle, not just a heap pointer. But unlike unique pointer and like polymorphic allocators, the custom deleter is not part of the type. It is not a template parameter, it is a constructor argument. So even if you store an array or some special resource, you often need to explicitly specify the deleter at construction time. And the question is why? Why is shared pointer designed this way? The answer is because shared pointer already needs a control block anyway. A shared pointer cannot exist without a control block because reference counting requires shared state, so we already have this heap allocated structure which stores the reference counters and destruction logic. That means we do not need to complicate the type system. With unique pointer, the deleter is a part of the type because unique pointer itself is the entire ownership mechanism. There is no separate blocks. But for shared pointer, we already pay the price of the control block so we can simply store the deleter inside it. And that is exactly what happens. So conceptually, shared pointer stores a pointer to the control block and a pointer to the data. And the control block contains the reference counter and also the custom deleter. So the deleter becomes runtime information, not compile time information. And this is why shared pointer can have a custom deleter without changing its template type. And this remains true even if the make shared case, even if the object lifetime itself is allocated inside the control block, the deleter still lives there as well. Same for aliasing constructors. Even if the shared pointer points to a sub-object inside the allocation, ownership is still controlled by the same control block and custom deleter just works. So the control block remains the true owner and it contains everything needed to destroy the resource correctly. And now at this point, this picture is already much closer to reality, but there is still something missing. So there are really two equivalent layouts. Either the data is separate or it's embedded into the control block, like this or this. It's no matter. Uh, but the deleter also lives here in the control block because the control block is the entity that actually owns the resource, but there must be something else in this control block to make stood bad weak pointer exceptions possible. And now finally I can ask the uncomfortable question. What are the main problem caused by copying and reference counting when working with the shared pointers? And at first glance, shared pointers looks like great solution. Not without like sharp edges, but great. You can copy it freely, pass it anywhere. Memory management becomes automatic. Okay, it turns your C++ more into the Java, but so what? Maybe I do want exactly this kind of C++. But the more you use it, the more you start paying for that convenience. Copying becomes cheap, so you start copying it everywhere. Ownership becomes unclear, lifetimes become unpredictable, and the biggest conceptual problem is that reference counter naturally create graphs which contains closed cycles. So shared pointer can easily create memory leaks, even though it was invented to prevent memory leaks. Let me show how. The classic problem is two cyclic pointers. There we have two nodes, master and slave, and each reference count 1. Then slave stores a shared pointer to master as its parent, so master now has count 2. Then master stores a shared pointer to slave as its left child, so slave now has count 2. And now we leave the scope. Both local shared pointer variables are destroyed, so both reference counts decrease by 1, but they do not reach 0, because master still owns slave and slave still owns master. So they keep each other alive forever after this function ends. And this is the worst kind of leak. A leak that looks perfectly correct at the level of local code. Nothing crashes, nothing looks suspicious, but the memory is never released. This kind of bug is extremely hard to debug. I have personally seen cases where such a leak was not even reproducible all the time because it depended on how objects were connected at runtime. Namely, I saw this inside the LLDB debugger. So yes, shared pointer prevents double delete, but it introduces a new failure mode, cycles. And what can be done with cycling shared pointer? And the standard solution is weak pointer. A weak pointer does not participate in ownership. It points to the same control block, but it doesn't increase the strong reference count. So here, we change only one thing. Parent becomes a weak pointer. Now slave can refer to master, but it doesn't keep master alive. So master still has count 1, not 2. And when we leave the scope, master is destroyed first, because its strong count reaches 0, then slave destroyed as well, so the cycle is broken and the leak disappears. Shared pointer means I own it, weak pointer means I can observe it, but I do not keep it alive. And now there is a consequence for this. A weak pointer cannot be dereferenced directly, because it might refer to an already destroyed object. So if you have a weak pointer, you must first convert it into a strong pointer. That is done with lock method. Lock checks whether the object is still alive. If it is alive, it returns a shared pointer that temporarily keeps it alive. If it is already dead, lock returns an empty shared pointer to null pointer, and only after that you can safely dereference it. Now notice that weak pointer does not magically solve your design problems. If you lock it at wrong time, or if you keep the return shared pointer for too long, you can still recreate the same lifetime issues. But at least now the lifetime extension is explicit and controlled. And here's another very important property. A weak pointer cannot dangle the same way as raw pointer. For example, imagine a function that creates a shared pointer locally and returns it as weak pointer, and the shared pointer dies at the end of the function, so the object is destroyed. Now, the weak pointer still exists, but it becomes expired. It doesn't become a dangerous dangling pointer. Instead, expired will return true and lock will return null pointer. So weak pointer gives you a very strong tool. You can safely detect whether the object still exists. And this is something raw pointer simply cannot do. And how weak pointer can do this? How do weak pointer knows that corresponding shared pointer expired? And let me finally show you the true picture of how shared pointer is structured internally. So how is weak pointer implemented? The idea is that control block has not one counter, but two. One is the strong reference counter for shared pointer, and the other is a weak reference counter for weak pointer. As long as the strong counter is non-zero, the object is destroyed. The object stays alive. When the strong counter becomes 0, the object is destroyed. But the control block is not destroyed immediately. The control block is destroyed when weak reference counter reaches 0. So if there is a block without any strong shared pointers left, but with some weak pointers left, it have this data cleaned up, but the control block still persists. And weak pointer works this way and is the standard way to break cycles and also a general tool for safe observation without ownership. And now here is small teaser from multithreaded programming. Shared pointer has a method, useCount, which returns the strong reference count. And someone wrote this helper function, do if single. The idea is simple. If this shared pointer is the only owner, then we can safely perform some action. And at first glance it looks reasonable, especially because the reference counter is atomic. But if you ever see code like this in a multi-threaded program, you should be extremely suspicious. The moment you check useCount, you get a number, but you do not get any guarantee that the number will still be true one instruction later. Like between two lines of code, there's any space. Okay, and another thread can create a new shared pointer immediately after the check. So we checked. You go to this section, but while you do it, another thread locks weak pointer. And boom, now you have two and you perform an action. And now let's recall the weak pointer model again. If there are no strong references left, then the data object is destroyed, but the control block may still live as long as weak pointer object exists. And in that case, the data pointer inside the control block becomes null, so weak pointer can detect that the object is expired and gone. That is why weak pointer can never truly dangle. Even if the object is gone, the control block still exists and still contains the counters. And only when both the strong and the weak counters become zero, the control block is finally destroyed. So weak pointer is not raw pointer, it's more like safe handle to the control block. But now here's an interesting twist. What if shared pointer was created via make shared? In that case, the object may be stored directly inside the control block allocation. And now we get a strange effect. Even after the last strong reference is gone, the object is destroyed, but the memory where it used to live still remains inside the control block. Because the control block may stay alive for weak pointers, so the memory cannot be released. This is a serious argument against make shared. With shared pointer of q of t, the object and the control block are separate allocations, so the object memory can be freed immediately when the strong count reaches 0. But with make shared, the control block and the object are tied together, so the lifetime of the memory is effectively extended until all weak pointer references are gone. This is one of those cases where make shared is not just a stylistic choice, it's a real design decision with trade-offs. So now let's step back and compare make unique and make shared. Make unique has almost a purely stylistic feature. It improves readability, prevents writing wrong U, and it improves exception safety. Exception safety is important here. Look at this function call. If we manually create two unique pointer objects from two new expressions, the compiler before C++17 was allowed to evaluate the arguments in an order that can lead to leak, like new of t1, then new of t2, then construct this unique pointer, then construct this unique pointer. The make unique version fixes this completely, because now compilers are no longer allowed to redirect this way. Our compilers may only allow redirect the arguments on the same function level. So the make unique version fixes this completely because each argument becomes a fully formed smart pointer expression. So the safest advice is simple. If you create a unique pointer, always use make unique. And the logic applied to shared pointer is like more non-trivial. If we construct shared pointer directly from U inside function call, we can again run into exception safety issues, at least before C++17. But now there are also additional arguments specific to shared pointer, because make shared performs a single allocation for both the object and the control block, so it can be significantly faster and more cache friendly. On the other hand, we just discussed it can extend the lifetime of memory in surprising ways if weak pointer is unsolved, is involved. So unlike make value, make shared is not just new nicer syntax like some sugar. It has both strong arguments pro and strong arguments cons, strong arguments for and strong arguments against. Okay, and now there is a famous example from effective modern C++ by Scott Myers, a caching factor. The idea is elegant. We have a static unordered map from IDs to weak pointer, and when someone requests the object, we try to log the weak pointer. If the object still exists, log returns a shared pointer and we reuse it. If the object is already gone, log returns null, and we create a new object, store it in the cache, and return it. Though sure, the cache does not own the objects. If It only remembers them if they still exist somewhere else. And the moment all external shared pointer references disappear, the object is destroyed automatically, and then the cache entry becomes expired, and the next request will recreate the object. This is a very nice pattern. Weak pointer gives you a cache without forcing global ownership. But of course, it has some subtle issues. For example, the map can grow forever because expired weak pointer entries stays in the cache unless you clean them up. So we still need some maintenance strategy. And now, here is the teaser problem. Thread safety. Every time you see a static or global variable in code, you should immediately think about concurrency, because this cache is a shared mutable object. Multiple threads can call getObject at the same time. They can access an ordered map concurrently, modify it concurrently, and corrupt it. And even if weak pointer and shared pointers themselves are thread safe in terms of reference counted, the unordered map is not. So this function is not thread safe, and in real program it will eventually explode. A simple fix is to add a mutex. We create a static mutex next to the cache, look it at the beginning of the function, and then perform the lookup and insertion under the lock. This is not the most scalable design, but it is correct. And this is already a good lesson that shared pointer solves lifetime issues, but it doesn't solve synchronization issues. Ownership is not the same thing as thread safety. And now a final discussion question. Can we use unique pointer of char square braces instead of string? And what about shared pointer of char square braces? In principle, yes. A unique pointer to a character array is a perfectly valid ownership wrapper. It can be useful for fixed site buffers or manual string building. But it is also very low level. You lose length tracking, you lose most of the string interface, and you lose a lot of safety, whatever safety is in C++. So it can work, but it is not a replacement for string and normal code. But there is an interesting idea. Shared pointer can actually be used to build a simple form of cow strings. For example, shared pointer of const string is a trivial and fairly simple form copy and write. And you can share the same string between multiple owners, and when you want to modify it, you simply create a new string object and publish a new shared pointer. So you get cheap sharing and safe immutability. And this is a nice example of how shared ownership can be used as a design tool, not just as a memory management trick. All right, and that brings us to the end of the lecture, and here's the bibliography. The C++ standard, Stroustrup, Herbsaters, Code Mars, Usutis, and so on. Smart pointers are no topic, but they are still extremely relevant. And in particular, we already saw several places where ownership decisions force design decisions. And I wholeheartedly recommend this talk of Herb Sutter, Leak Freedom in C++ by Default, where Sutter is really inspiring. He observes every existing smart pointer in details, and even invents some his own smart pointers like deferred pointers. If you haven't seen it, please do. And today we saw several places where ownership decisions force design decisions. And that is exactly the bridge to the next lecture. Next time we'll start talking about dynamic polymorphism, and we will revisit virtual functions, and then we will discuss how this mechanism interacts with memory. With memory management, with object lifetimes, with everything like that. But for today that's all. Thank you for watching.